we are on to derivatives. Okay, so the first thing we are going to look at is the tangent line problem. Okay, if I have a line like you looked at in Algebra 1, and I want to know the slope of that line, we have a formula for that, and that's not a problem. Okay, but if we have a curve, if we want to find the slope, it's not a constant slope. So sometimes, like let's say down here, right, the slope wouldn't be so steep, but then if we move up here, right, we're going to have a much steeper slope, okay, of the line, right? And so we can't really find the slope of the line. We can only find the slope of the tangent line, okay? And I apologize for anything that sounds like a typewriter in the background. That is the guinea pig drinking. You may have noticed by now that I have plenty of animals. Anyway, so if we want to find the slope of the line tangent to point C, okay, so in other words, this, right, that would be a little difficult because we only have one point on the line, and we know that in order to find slope, we need 2 points, right? Change in y over change in x. Okay. And, well, why do we even care about that? Okay, and the reason we care about that is because that is going to be our rate of change at a given point, okay, our slope at a given point. So we will care about that. But we just said we can't calculate slope because we don't have 2 points. Okay. However, possibly we could estimate the slope of the tangent line at a point by using secant lines. Now, if you don't remember what secant lines are, they just intersect a curve at 2 points. A tangent intersects at 1 point, secant at 2 points. Okay. So if I want to find the point or the slope at point C, I don't know the slope of that tangent line, but let's say I used this line. Okay, well, I could find the slope there, right? I do change in y over change in x, and I would get a slope. Okay, well, an even better estimate is instead of using Q to NC, I could use RNC, right? That's even closer to the tangent line at a more accurate slope. Okay, even closer than that, I could use S, right? And the slope of that tangent was better the slope of that secant would better approximate the tangent, okay? Or even better than that, I could use the slope between T and C, okay? As I get closer and closer and closer to C, it's approaching the slope of the tangent line. You may now recognize this as a limit. So essentially, we're saying that as the limit between our point and C gets to 0, okay, we can find the slope of a tangent line. Okay, so we'll look at that a little more on this next page. Okay, so looking at this picture here, okay, this is basically what we were just looking at on the first page. Okay, this right here, okay, is our delta x. Delta just means change, so it's our change in our x value. Okay, so if this right here is point C, this up here is point C plus delta x. So in other words, it's C plus a little bit more, however much further we're over on the x-axis. Okay, we want those to approach 0 because we can keep drawing secant lines closer, 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 right, until we get to the tangent. And that would be when delta x is 0. Okay, all right. Then on the other side here, so up and down, okay, that would be our change in y, okay, or delta y. Our smaller y coordinate is f of c, so in other words, I'm evaluating the function when x is c, okay, and our larger y value is just f of c plus delta x because that's our x value. Or our input, that's our input value. When we input that into the function, our output value would be just the function evaluated at that quantity. Okay, so using that, okay, to find the slope of a line, we are just going to divide the change in y by change in x. That's what you've been doing since Algebra 1. Okay, it just looks a little different now. So we're going to say that m, or the slope of that secant line, is change in y over change in x, or f of c plus delta x minus f of c all over delta x. Okay, so in that case, the slope of the line tangent to the graph of f at that point can be written as the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. Okay, and that's basically just saying that that distance between our point that we want to find the tangent at and the other point on the secant line is just getting closer and closer and closer to 0. Okay, when they're at 0, that would just be the tangent line. Okay, so this is also called the slope of the graph at that point, or we could also call it the derivative of a function at a point. We will be using derivative a lot. Really what derivative is just slope. Okay, but it's a little more complicated because we can't just easily find the slope of a curved line. Okay, we need to find the derivative. Okay. And then we can also use another formula to find the derivative at a point, and that formula is the limit as x approaches c of f of x minus f of c all over quantity x minus c. Okay. If you would like to see a proof for why we can use that formula and how the two are related, I have included a link that you are welcome to go to. Once we do a few of these problems, they'll make a little more sense than just looking at the theory. Okay, so for example 1, let's use our formula for the derivative at a point to find the equation of the line tangent to f of x equals x squared at x equals 2. Okay, so using our formula, okay, we can say limit as delta x approaches 0, okay, so as the change in x approaches 0, of 2 plus, actually I'm going to zoom in I think here. Okay, that's better. So limit as delta x approaches 0 of 2 plus delta x quantity squared minus 2 squared all over delta x. Okay, so that is just plugging in x plus delta x into our function. Okay. All right. So now when we evaluate this, we can FOIL everything out. So we have limit as delta x approaches 0. Okay, we get 4 plus 4 delta x plus delta x squared minus 4 all over delta x. Okay, well conveniently these 4's cancel. And then if I divide through by delta x, these guys cancel. One of those cancels. Okay, so that leaves us with the limit as delta x approaches 0 of 4 plus delta x. Well, when we evaluate that limit, okay, by direct substitution, we get 4. So we will say that the derivative at x for f of x equals x squared is 4. Okay. The other option for us is instead of using that formula, okay, we could have used our second formula, okay, the one I showed you at the end. Okay, and for that we'd say limit as x approaches 2 of x squared minus 4 all over x minus 2. Okay, so that is limit as x approaches c of f of x minus f of c all over x minus c. Okay. All right, so we can factor x plus 2, x minus 2. Okay, conveniently, these cancel, so we end up with just the limit as x approaches 2 of x plus 2, and that is also 4. So either of the options on the last page will work, okay, and it's really personal preference which one you prefer, okay. All right, and then it says, let's use our formula for the derivative at the point to find the equation of the line tangent. Okay, so now we have our slope. Right, we know our slope is 4, okay, and we know our x value is 2. Okay, so if we put 2 into our function, we get 4 out. Okay, so basically we have a point and we have our slope. So we can just plug that into point slope form. Okay, and that would be y minus 4 equals 4 times the quantity x minus 2. Okay, and if you wanted, you could put that in slope-intercept form. You do not need to. Okay, either option is fine. But now we know that the slope of the tangent line at x equals 2 to the curve of f of x equals x squared is y equals x minus 4. Okay, and you could graph that. Okay, if you graph that, and you could do it in your graphing calculator. Okay, I know that y equals x squared is a parabola, right? It should look something like this. Okay, and I know that y equals 4x minus 4 has a slope of, let's see, or y-intercept of negative 4 and a slope of 4. So it's going to cross here. Okay, and although my drawing isn't great, okay, it should meet up at when x is 2. So it would be 2 at 2, 4. Okay, that point should be on both, and you would see that y equals 4x minus 4 is, in fact, a tangent line to that curve. Okay, now we are going to look at our next example. And I'm actually just going to write the formulas at the top just so we don't forget them. Okay, there they are. Okay, just that way we have something to reference. Okay, so now we're going to use our formula for the derivative at a point to find the equation of the line tangent to f of x equals root x at x equals 9. Okay, so we are again going to use both of these methods, both formulas, in order to find the derivative. And you will be able to choose which you would prefer. I just want you to be comfortable, or at least have seen both. Okay, so the first one, we have the limit as x, or delta x, approaches 0 of f of c plus root x, c plus delta x. I'm going to put root c is 9, okay, plus delta x, minus f of c, that is square root of x, all over delta x. Oh, I'm sorry, it's square root of 9. Let's fix that. Okay, square root of 9. Okay. All right. So now we have limits as delta x approaches 0 of root 9 plus delta x minus 3 all over delta x. Okay. And we know that if we just evaluate this, if we do direct substitution, we would get 0 over 0. So, well, we know what to do with that, right? We're going to rationalize. So let's multiply by root 9 delta x plus 3 over root 9 plus delta x plus 3. Okay, when we multiply that out, we get limit as delta x approaches 0 of 9 plus delta x minus 9 all over delta x times quantity root 9 plus delta x plus 3. Okay. All right, well, conveniently these 9's cancel. Our delta x's cancel, so we're left with 1 on top. Okay. If we now do direct substitution, okay, we get 1 over, let's see, root 9 plus 3, that is 1/6. Okay, so our derivative at 9 is 1/6. That means that our slope is 1/6. Okay. If you didn't like that method of doing it, okay, we could use our other definition of the derivative. Okay, so in this case we have limit as x approaches 9, okay, because that's our c value, okay, of root x minus root 9 all over x minus 9. Okay. Well, again, we're in the same position. If we put 9 in, we get 0 over 0. Okay, so we need to rationalize. So we have root x plus root 9 over root x plus root 9 Okay, that gives us, let's see, limit as x approaches 9 of x minus 9 all over x minus 9 times quantity root x plus root 9. Okay, conveniently these guys cancel out. We're left with 1 on top. Direct substitution now says that we do 1 over root 9 plus root 9. That is 1/6 as well. Okay, so again, either option works. It's really personal preference. Okay, but that now tells us, let's see, because we want to find the equation of the line. Okay, so now we know that the slope is 1/6. Okay, if we plug in 9 as our x value, we get out 3 as our y value, so we have the 0.93. Okay, and we can now use that to write an equation. So using point slope form, we have y minus 3 equals 1/6 times quantity x minus 9. Okay, so that is perfectly acceptable. That is the slope of the tangent line. Okay, but if you wanted, you could write it in slope-intercept form. That would give you y equals 1/6 x plus 3/2. Okay, and this is the last page you guys will be doing today using these notes, and then we are going to spend plenty of time practicing this in class. I want you to see it, but we're going to spend lots of time going through it. Okay, so we talked about the derivative at a point. The derivative of a function provides us with the slope of a tangent line at any point on the curve. Okay, so not just at one point, it's a formula for the slope at any point. Okay, and the derivative of a function at of a function f at x is given by f prime of x equals limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So it looks very similar to derivative of a point. Okay, there's only a little bit difference. Okay, and of course that's provided that the limit exists. Okay, and for all x for which this limit exists, f prime is a function of x. Okay, so notation for derivatives includes sometimes you might see f prime of x, sometimes you might see dy over dx, sometimes you might see d over dx, f of x. Okay, there's a lot of different notations, and you want to make sure that you are comfortable with all of them. Okay. All right, so I'll go through 2 examples, and the rest we will do in class. Okay, so find f prime of x for f of x equals x squared. Okay, so let's plug that into our formula. Okay, if we do that, actually I'm going to zoom in again so we have space. Okay, if we do that, we have f prime of x, okay, should be equal to the limit as x approaches 0, okay, of x plus delta x squared, okay, so that's inputting x plus delta x into our function, minus x squared, that's f of x, right, all over delta x. Okay, so we just have to find out what this limit is. Okay, so that's the limit as x approaches 0. When we FOIL this out, we get x squared plus 2x delta x plus delta x squared minus x squared all over delta x. Okay, well, these x squareds cancel out. Okay, and then we're dividing through by delta x, so that cancels, and one of those guys cancel. Okay, that leaves us with the limit as x approaches 0 of 2x plus delta x. Okay, well, when we plug that in, that 0 in, okay, we do direct substitution, that just gives us 2x plus 0 or 2x. Okay, that tells us that the derivative of that function is 2x. Okay, it's okay that a variable exists there because what that's telling us is that's the formula for the slope at any point. So in other words, if I want to know what the slope was when x was 3, I would plug it in and say, okay, the slope is 6. Okay, if I wanted to know, well, what's the slope of the tangent line at x equals 7, I'd plug it in and say, okay, the slope of the tangent line at x equals 7 is 14. Okay, so that is the formula for the slope at any point. Okay, one more example. So now we have find f prime of x, or find the derivative, for f of x equals root x. Okay, so we're going to do the same thing we did before. So f prime of x equals the limit as x, or delta x, approaches 0 of root x plus delta x minus root x all over delta x. Okay? So we need to rationalize. Okay, so we're going to multiply by x plus delta x plus root x all over root x plus delta x plus root x. Okay, when we multiply that out, we get limit as delta x approaches 0 of x plus delta x minus x all over delta x times quantity root x plus delta x plus root x. All right. Well, these x's cancel, delta x's cancel, we're left with 1. Okay. Now, using direct substitution, we get 1 over root x plus 0 plus root x. Okay, that is the same thing as 1 over root x plus root x, which is 1 over 2 root x. Okay, so what that tells us is that the derivative of this function, okay, is 1 over 2 root x. Okay, and that is the end of that. So we are going to be doing plenty of practice with this in class. I just wanted you to kind of be exposed to it and get the idea of what we're trying to do. But come in with questions and we will do plenty of practice.